In this video, we cover how to take derivatives of exponential functions. Before we get into the rule for taking the derivative of an exponential function, let's recall what an exponential function is. An exponential function is a function of the form f of x is equal to the b to the x, where b is greater than 0. Okay, so all of these exponential functions have their variable up in the exponent. All right, so f of x equals 6 to the x is an example. And a very special example of an exponential function is f of x equals e to the x. That's the natural exponential function, and hopefully you remember that from pre-calculus. All right, so the derivative of an exponential function, all right, so given an exponential function that looks like this, b to the x, f prime of x is going to be ln b times b to the x. All right, so let's apply this rule to this problem right here. So if f of x is equal to 6 to the x, f prime of x is going to be ln 6 times 6 to the x. And hopefully you can recall that ln 6 is just a constant, and you can calculate that on your calculator. All right, so let's do the same thing for f of x is equal to e to the x. F of x is equal to e to the x. All right, f prime of x then would be ln e times e to the x. And if you calculate ln e, or you might not even need to calculate ln e, you may recall this from pre-calculus, but ln e is just 1. All right, so this would just be equal to e to the x. So that is our general rule for the natural exponential function. The derivative of e to the x is just e to the x. And that's quite a cool thing, actually. This is the only function whose derivative is exactly the same as the original function. So Theorem 3.14 says, let capital E of x equal e to the x, or the natural exponential function. Then the derivative of that function is also just e to the x. Now note, though, that this only works if there's a single x in the exponent, all right? If there is something more in the exponent, okay, so if there's a quantity in the exponent, we're actually going to have to apply the chain rule. And let me remind you of a similar situation so that you can see why this is. Remember when we had f of x is equal to sine of x. The derivative of that was just cosine of x, right? But that only worked when it was a single x here. If you had a quantity there, so sine of x squared, we actually had to apply the chain rule because this is the composition of two functions, isn't it? So the chain rule said then that we had to take the derivative of the outside function, so cosine of x squared, and then multiply it times the derivative of the inside function, so times 2x. A similar situation happens here. So if I have simply e to the x, the derivative is just e to the x. But if I have a quantity in the exponent, so let's say e to the x squared plus 4, then to take the derivative, I apply the rule as it is, so I say e to the x squared plus 4, but then I also have to apply the chain rule by taking the derivative of that exponent. So g prime of x would be times 2x. All right, I'm taking the derivative of this term. So I can simplify that by writing 2x times e to the x squared plus 4.